So this video is going to talk about how do we know we're at an equivalence point in a titration. So let's start with a titration. You all have done a number of them in general chemistry, and ultimately we have focused on acid-base titrations. We're going to stay with acid-base titrations in this chapter and for now. And so bottom line, in an acid-base titration, you have a solution of unknown, a titrant, and you slowly add it to a known concentration from a burette. And you did that in 111. And when the reaction was complete, you reached an endpoint. And how you knew that in 111 is that you had some sort of color change, is what we generally denoted. So we had a color change, and that denoted our endpoint. An indicator is what you put into the solution in order to know that. At the very beginning, we always said, make sure you have that indicator, because if you don't, you're not going to know when you've reached your endpoint. And an indicator is a chemical that changes color when the pH changes. So ultimately, that endpoint is the equivalence point. Where you titrated to, that faint color change, is where you ended up in terms of a titration's equivalence point. So when you reach the equivalence point, what is true for the solution in the flask is that the moles of H3O plus, the moles of acid, are equal to the moles of the hydroxide or the base. This is extremely important conceptually. So when you've hit that color change, that is the point you've reached equivalent, and the moles of your acid and the moles of your base are the same. Now the pH of the equivalence point varies depending on what kind of acid and base are reacting. So let's start by looking at a couple of things. So the first thing I want you to do is write the net ionic equation for the reaction between hydrochloric and sodium hydroxide. Now notice, net ionic. So what I would like to ask you to do is pause the video right now, write that net ionic. If you have to go back into chapter 4 notes to do it, that's fine, but I want you to take the time to do it. That's active learning. Then start the video again, and you will see me working out that part of it. So I'm going to go to my notebook page now, so go ahead and pause and do that. And I'm going to show you what that net ionic looks like. So we have our strong acid reacting with our strong base. For our this is actually going to be a titration problem, but we're going to write that net ionic. Should this be a straight arrow or a double arrow? Should be straight because we have both strong acid and strong base. And then we have water and sodium chloride. So for a net ionic, we only want those ions that are participating. So knowing that this is a strong acid, it will completely disassociate by definition. Sodium hydroxide is a strong base, so it will completely disassociate, and so you see the aqueous. We have water. Any solvent in itself is a liquid, and sodium chloride, if you look at your solubility chart, is completely soluble. So I'm going to write a note, completely soluble, completely ionizes. So what that lets me know is I have H plus Cl minus, and just to save space, I'm not going to put the phase labels on, but you should. And then of course water doesn't break apart because it's a liquid, it's not aqueous. And then we have sodium plus and chloride minus. So this would be our ionic, but it is not our net ionic. We only want the ones that are actually participating in the reaction. So we look to both sides to see what's in the same phase and in the same form. And we get rid of my sodium and my chloride, and you'll see that we have H plus OH minus yields water liquid. That is my net ionic. Now, we're going to go back to that problem, and the next one says, or reads, what is the pH of the solution that is formed by titrating? So now we're doing a titration between sodium hydroxide and HCl. The first thing I always ask you all is, if I put the two together, is there going to be a reaction? We've already answered that because we showed on that previous problem that when we add our acid and our base, both of them are strong, and yes, we have a reaction. And the question also is this solution at equivalence point? Well, the only way we're going to know is we've got to figure out what's left at the end after reaction. So we're going to come back to this problem here, and we notice we have H plus. So we've got to figure out what's initially in my flask in moles. So we come back, and what's initially in my flask at moles, we have 0.012 molar and 740 mils. So we come back to that problem, 0.012 1, 2, I believe. I'm going to double check that again. 0.12 molar. And we want to get it to just moles, so we've got to convert our 740 mils to 0.740 liters, and that's going to give me how many moles of H plus I start with. And then we've got our sodium hydroxide, and 0.205 moles, and we multiply it by the volume. And then the water, we don't have any to begin with. So at this point, we would ask the same question. Do we have a reaction? Yes, we've already answered that. Now that we have moles, we would ask limiting reactant. So reaction, question mark, yes. Limiting reactant, question mark, yes. So you should know how to proceed. So again, I want you to stop the video now, and I want you to go and work this, the rest of it. See what you can find out's left, and then the pH. When you come back, I'll continue it. All right, so we're going to continue working this problem. I'm going to finish putting in my number of moles. So for my hydrochloric, I end up with 0.00888. And for my potassium hydroxide, or hydroxide, rather, I have 0.09225. That's the number of moles I found. And so when we look at this, they're both 1 to 1. So I'm going to subtract out my limiting reactant, which is my H plus. And normally I would add to the water on the other side, but that's not going to affect my pH ultimately. But we would also, I'm just going to be a little deliberate and show that so that later you won't forget that. And so we have no H plus left, but we definitely have hydroxide left. We have 0.08337 moles of hydroxide. And then the last question, just like what we were asking before when we had those buffer problems or reaction problems, we're going to ask what kind of solution is left. So what kind of solution do we have? And so when we look at this, we've only got 3 options. Buffer. It's definitely not a buffer because we have a strong base and nothing else. And then the other 2 options were, do we have a Ka or a Kb? Do we have a weak acid or a weak base? No. So that means that there must be more options. So there are 2 other options, and that is we could have a strong base in solution, or we could have left over just a strong acid. And what you'll notice is we've got the strong base. And we learned last week in class that when we have a strong base, that all of it goes to hydroxide, which we see already. And so we can find the pOH by taking the negative log of the concentration of the hydroxide. Now here's where you've got to take a little bit of pause and go back and say, all right, I need to have a concentration value here. So we've got to have concentration right there. So in order to make this a concentration, I need to divide the moles of hydroxide by the total volume. The total volume is going to be what was totally added together. So in this case, it's going to be our 0.450 plus the 0.740, because remember, I added 450 mils of hydroxide and 740 mils of hydrochloric. Both of those added together, my total volume. So I've got to divide by that. When I do that, I end up with the concentration of 0. And I'm going to need a little bit more space right here. And so I have 0.07006 molar. And that's my pOH. So then I can calculate that pOH. It ends up being 1.155. And then when I find my pH from 14 minus that, I end up with a pH of 12.85. And that's my answer. But I wanted you to see that all the way through. So we found the pH, and then the next question is, are we at equivalence? Well, how do we identify whether we're at equivalence? Exactly. We look at, do we have the same number of moles of hydroxide and the same number of moles of hydronium left over? Do I have the same moles of acid and base left over after reaction? If we look at it, no, we have 0 left of H plus, and we have some hydroxide. So we are not at equivalence. To be at equivalence, I would have to also have 0.08337 moles of H plus left, and I don't. So we are not at equivalence. That's how you'll identify whether at equivalence. You put the items together, your acid and your base, they react, you find the limiting reactant, you find what's left over, and then you have to figure out, do I have zero of both? And do I have the same amount of both? If you had zero of both, you'd be at equivalence, right? So look out for those key information points, and that is essentially how you determine equivalence point.